Hello and welcome to this lecture 3 of week 10 of the course on control engineering. My name is Ramkrishna. I am from electrical engineering, IIT Madras. One question that we always, or one assertion we always make, is that we are restricting ourselves in this course to linear time invariant system. And say we may just look around and say, well, most systems are non-linear and therefore they may not satisfy the property of superposition and homogeneity. So, as simple as if I would write the Newton's second law states that that the force is not ma, but it is the rate of change of momentum. Why does it become ma? So, that is because we consider that momentum is mass times velocity. Of course, this does not hold, this holds only in the for maybe smaller velocities, but in the relativistic setting you may see that the momentum and mass are not linearly related. Now, once they are linearly related, this becomes m dv by dt. dv by dt is acceleration. So, this is how we popularly know it, and therefore, the energy, the kinetic energy, we call it as half mv square, even though if I go from the Newton's laws, this will be p square by 2m. So, we should write in terms of momentum, which is the fundamental building quantity. Similarly, if I look at the energy of an inductor, we say that is half L I square. That also comes because we assume that the flux, that the current is proportional to the flux, and that I equal to some L, sorry, I think it should be the reverse, that flux is proportional to the current, and in the linear setting I can just assume that phi equal to L times I, and therefore I can write my energy in terms of half L I square, even though fundamentally they may not be linearly related. A linear relation, we say V equal to I R, even though we even though this may not be true. All the definition of a resistor is that V times I must be greater than 0, that it must dissipate power and so on. Okay. So, the assumption so far we have made is that the plant can be represented by a linear transfer function. Of course, when I say it is a kind of a redundancy here. Transfer function is essentially linear. And why do we study these linear techniques? And how do we therefore ignore the entire world of nonlinear systems and say, well, I am happy doing the linear systems theory? What happens if a nonlinear system knocks at my door? It says, so we will see the first method that Lyapunov stability. Of course, we will not go into the details of this. A large amount of Lyapunov literature is can be found in nonlinear systems analysis. Maybe a full course on nonlinear systems would have emphasis, a lot of it on Lyapunov stability. And of course, if you look at any control literature, any paper which talks of stability has to talk in the context of Lyapunov. So, that is the kind of the most important contribution starting from the work of 1892, where the dynamical systems world had a very nice view of looking at stability of systems. So, what in the first method, and that's what we will do the first method, we will not look at the second method, even though briefly I will mention what it means. In the first method, the stability was based on the linear approximation. As I said, in one of the earlier lectures when we were talking of models and how observations build models, and you challenge those observations and you go on to build more general models. Say if I just look at locally around me, I stand on a football field or on a cricket field, I would say that the earth is flat. Like I don't have a football field which is like this, right, or a cricket pitch which is like this, or I don't construct a building when assuming that the earth is curved and therefore my design will be a little different at different parts. So, in my area of sight or my area of operation, I can fairly assume that the earth is flat. Okay. So, this is what happens in the linear approximation, right. So, and then how do we understand stability also from the linear approximation? Can I look at some behavior via linear sense? Can some behavior of nonlinear systems be replicated via some of its approximation? So, this is what we will look at the first method of Lyapunov about the linear approximation and therefore stability analysis. Second method describes the equivalent of finding a scalar function that describes internal energy stored in the system. If I look at if I take a fan, for example, it is operating at full speed, I switch it off. What happens is that the energy dissipates and it goes to its natural equilibrium. So, which essentially means if I write down the equation for energy, this will always be less than or equal to 0, that the energy function keeps on decreasing. In general, if I look at a system, I associate some quantity called energy to it and I look at its energy behavior without any input. If the energy monotonically decreases, I can say that the system is stable. While for example, I take a pendulum at some say initial condition of 30 degrees, it will oscillate and then slowly come back to its equilibrium position. Okay, so, the energy dissipates, whereas something different will happen when I start from the top position, right. So, I start from here. What I see here is that the if I just perturb it from its equilibrium position, it just goes very far away from its equilibrium position, also meaning that the energy increases along the system trajectories. Okay. So, if such a function is constructed which in the physical system world has the notion of energy, and if the function decreases monotonically, in calculus it would mean that the derivative of the function is negative, then the function will eventually drain, the energy will eventually drain away and the system will come to rest at the equilibrium point. Okay. So, largely, so if I say, let me take a very simple system, say x dot is minus x and let me associate an energy to it, say half x square. That is what we write, half mv square, half cv square, and let's say it is half x square. Now, I will call this E. What is it that if the derivative of the function is negative, let me find what is dE by dt. dE by dt is twice x dot. This is x dot is minus x. So, this will be minus twice x square, which is always less than or equal to 0, and it comes to 0 only when it is at the equilibrium point. So, here x equal to 0 is the equilibrium point. I have not yet talked in detail about equilibrium points, but we'll just quickly try to understand that from the energy point of view. So, which means the energy function is decreasing because the slope of E versus time, if I plot it, that will always have a negative slope. On the other hand, just take a system of the form x dot equal to x, and I say again I have an energy of the form half x square dE by dt is x dot. So, this will be, okay, there will be no 2 here, right, the 2 will disappear because of the 1 by 2. Okay. So, x dot this will be x square. Okay. X, so if I say dE by dt is x square, means this is a positive function, the slope is greater than 0, this is an increasing function all the time, and therefore, this system is unstable and this system is stable. Of course, this is all I will talk about in the second method, right, and then a course on full-fledged course on linear system theory or nonlinear control will tell you a lot more details on this. Okay, now what are the equilibrium points, right? So, and then why are we interested in equilibrium points? So, let us say I start with a nonlinear, with a system equation of this form, x dot equal to fx. So again now we are used to the state space language, x is a n dimensional vector, some initial condition and so on. So, equilibrium point, a point is said to be an equilibrium point if f of x star equal to 0. So, in the examples I had x dot equal to minus x, x dot equal to plus x, what I just do is I put f x equal to 0, which means x at what point is x f of x star equal to 0, this will be at x equal to 0 in both cases. Okay, which means that the system does not have any transients, right? It's in the steady state, that the position doesn't move, that the velocities might be 0 and so on. Okay, so now in a little more abstraction, if I look at the system like this, what I should be equal to here, if this is equal to 0, which means that I am equating the right hand side equal to 0, which means that x1 equal to 0, minus 6 x1 minus 5 x2 equal to 0. So, I put x1 equal to 0, this gives me x2 equal to 0, and therefore, the equilibrium point is x1 equal to x2 equal to 0. Okay. So, again this is a system of the form x dot equal to ax. So, can I say that whenever it is of the form x dot equal to 0 is x equal to 0 always the equilibrium, or is this the only equilibrium? We will do a little more analysis on that. Now, I will consider a pendulum equation, right. This is a pendulum without any friction. I am assuming that all the mass, acceleration due to gravity, the length, everything is equal to 1 because nothing changes. Okay. Now, look at this. The equilibrium points, I just said the right hand side equal to 0, x2 equal to 0, minus x2 minus sine x1 equal to 0, which means that sine of x1 equal to 0, means x1 is n pi. Okay. Now, the contrast here is that this system had only one equilibrium, and it was just the origin 0 comma 0. This system has multiple equilibrium, right. So, if the system is autonomous, okay, so this is what we are looking at, right. So, I am looking at solutions of f of x equal to 0. So, this system has multiple equilibrium. So, that could be 0 comma 0, x2 will always be 0, like the velocity will be 0, I have pi comma 0 and I have minus pi comma 0, and these are systems which are autonomous and also time invariant. Okay, now here I ask the question, is x equal to 0 always the equilibrium in the linear case? Well, then I go ask the questions to linear algebra, right. I have x dot equal to ax, equilibrium means I am looking at ax equal to 0. Now, what are the solutions to this? Okay. So, the earlier example of 0, 1, minus 5, minus 6 had a solution which was x1 equal to 0, x2 equal to 0, right, nothing apart from this, because A is invertible. So, suppose I have another A which looks like 0, 1, 1, 0, sorry 0, 1, I will say 0, 0. Okay, now, if I look for the solutions of the form Ax equal to 0, this would mean I am looking at x1, x2 equal to 0. Solving for this will give me x1, 0 times x1, so this will give me x2 equal to 0 and any x1, right. Any point of the form A comma 0 is an equilibrium point, right. How do you check that? 0, 1, 0, 0, any A 0 will be 0. So, this A could be plus 1, it could be minus 1, it could be plus pi 1000 and so on. So, if I just plot the equilibrium points when A equal to 0, 1, minus 5, minus 6, then there is only one equilibrium, that is the origin. Okay. Now, if I look at a situation where A, maybe I will do a different color, A equal to 0, 1, 0, 0, any A comma 0 is a equilibrium, which means x2 equal to 0. Okay, if I just say this is x1, this is x2, this any point on the x axis is a equilibrium point, right? Sorry, okay, how do I do this? So any point on the x axis is an equilibrium, and then this will now be called as a continuum of solutions or the continuum of equilibria. In the linear algebra language, this will be called as the null space of A. In the first case, the null space has only the trivial vector, that is 0 comma 0. In this case, the null space consists of all vectors of the form A comma 0. Now, what happens in the nonlinear case? We can have a continuum of equilibrium, right? So, I take this, equate this to 0, equate this to 0, and I end up with a solution that any point 0 comma x2 is a continuum of equilibrium. So, this will just be that x1 is 0 and x2 can take any values. So, that is precisely this point. Okay, nice. Can there be systems for which there is no equilibrium? Okay, let us look at this example. Equilibrium can be found by mu minus x1 square equal to 0, minus x2 equal to 0. Second one is fine, so I have x2 equal to 0. What happens to the first equation? I have x1 square equal to mu. Mu greater than 0, I am fine, right? I have, okay, it should be square root of mu, right? Mu greater than 0, I am fine. I have equilibrium points as plus minus square root of mu. Mu less than 0, I cannot define square root of, let us say, mu equal to minus 1. I cannot define this, right? Okay. And then there are also systems which do not have equilibrium points, right? Okay. So, this is nice, right? And why is analysis of equilibrium points useful? What we claimed in the first thing is that, well, I am looking at a linear approximation. Okay, now what I know here is that maybe this pendulum has multiple equilibriums 0 0, pi 0, minus pi 0. That is a point here, another point which is somewhere here, this will be pi 0, and another point which is, sorry, another point which is somewhere here like minus pi 0 and so on. Okay, so this is 0 comma 0, pi 0, minus pi comma 0. Okay, so what do we know about a simple pendulum, right? If I start with the downward position, I perturb it, it will come back to its equilibrium position after maybe oscillating for a while. If I take the inverted pendulum, I perturb it, it will just go away, right, from the equilibrium point. Okay. Now, let us look at this, right, this point 0 0, if I am anywhere around this point, let us say I am at this point, I just come here and settle down here. If I am around here, I come here and settle down here. Okay. Now, similarly around this point, if I am here, I just go away from this point. That I am here, I just go away from this point. If I will be here, I will just take this trajectory and go away. Okay. And similarly here, I will just take this trajectory and go away. So, around this point, in the neighborhood of this, all points come back to this point. Around the neighborhood of minus pi and plus pi, the points go away from the equilibrium point. Okay. So, the local behavior. So, what I am plotting here is, on my x axis is my theta, y axis is my theta dot. I am plotting how the position and the velocity vary. If you look at the pendulum, which is the stable pendulum, it starts from some arbitrary theta and say some arbitrary theta dot, it has to come back to its position. Both theta and theta dot will be 0 at the equilibrium. If I am here, I do a slight perturbation from plus pi 0 or minus pi 0, I will just go away from that. So, plus pi, maybe I am just measuring it this way as plus pi, and this I am measuring this as minus pi. Okay, they both kind of mean the same. So local behavior varies around the equilibrium points. Trajectories around 0, 0 point towards the equilibrium point. Trajectories around plus minus pi 0 point away from the equilibrium point. Can I therefore relate this to a stable behavior and an unstable behavior? And therefore, can we have a framework to analyze such behavior qualitatively? I mean, I may not be able to draw plots all the time and check what is going on. Okay, now a question that we could ask is, well, why are systems non-linear? Okay, now I start with a system. Of course, there is this logarithmic terms which makes them highly non-linear. Can I write this as, is this system equivalent to a linear system? System can be non-linear because somebody wrote it in the wrong coordinate systems. Okay. Now consider a normalized pendulum. Again, I am just assuming G equal to L equal to M, everything is equal to 1. So I just have this one, right. So theta double dot and so on. Can I write it as a linear system by some magic? Okay, so let us start with this system and say I do a coordinate transformation that Z1 is the log of x1, Z2 is the log of x2. Okay, so what is Z1 dot is 1 over x1, x1 dot. What is x1 dot is so this is 1 over x1, x1 dot is x1 log of x2. What is the log of x2? This is z2. Z1 dot is z2. Similarly, z2 dot will be minus 1, sorry, plus 1 over x2, x2 dot. What is x2 dot? This is 1 over x2 minus x2 log of x1 is now z1 plus x2 times u. What I am left with is the negative of z1, x2 goes away. So I will be left with plus u. Okay, so this is nice. This is in my familiar territory. With a system of the form z1 dot, z2 dot is 0 1 minus 1 0, z1 z2 plus 0 1 u, right, of the form x dot is a x plus b u, okay, with again the equilibrium being at 0 comma 0. Okay, what has happened here? I just apply a small coordinate transformation, and coordinate transformation we have done a lot in our geometry, especially from rectangular to polar and cylindrical coordinates and so on, and whenever we do this multivariable calculus. System could be nonlinear because somebody wrote it in the wrong coordinates. However, is this possible all the time? Well, maybe not, but this is one way to look at a nonlinear system. Okay, now start with this system and take an input of this form. So I have theta double dot plus sin theta plus d theta dot is u is sin theta minus theta star. This goes away, all I am left with, okay, maybe some other input, I can have some auxiliary input. So what I have is theta double dot plus d theta dot plus theta minus theta star is some v. Okay, so what have I done now is, this is the nonlinearity. I have killed the nonlinearity with the help of feedback, and not only that, the system now has an equilibrium at theta equal to theta star and of course theta dot equal to 0, which means I am starting with a pendulum, a nonlinear pendulum. With the help of appropriate control, first I kill the nonlinearity, second is I can also hold this pendulum arbitrarily at any theta star. It is not that I am only either doing the downward position or the upward position. I can apply appropriate control or to just hold it somewhere here, possibly just put a rotational spring here which will just hold it at that angle. Okay, so these are fine. The questions that can be asked is the following, right. So, is it always possible to do this transformation? The answer is no. Is it always possible to do this transformation? Again the answer is no. Are there conditions under which we can do this? The answer is yes. Of course, we will not go to those conditions now, that we will leave it for a course on nonlinear systems. Okay, so the first question is, okay, most laws we learn through physics are approximation of some nonlinear relationships. That was from circuits to as I said about the relation between mass and the velocity, voltage and current through a resistor, F equal to Kx and so on. So, it is therefore natural formulations could be nonlinear. Question that can be asked is, can one analyze the properties of nonlinear systems via their linear approximation, and how to derive those approximations, because it may not always be possible to find a coordinate transformation. Even if it is possible, what is that coordinate transformation may also not be very obvious. Is it possible to kill the nonlinearities by feedback? Well, in some cases yes, in many other cases it may not be. Are there any other easier methods? So, what do we do is we look at the process of linearization. What I know is that my phase portraits, so this is my phase portrait around the equilibrium points has lots of information. So, can I just restrict my system to analyze to can I just restrict my analysis of my system to just analyzing around the equilibrium points, right? Just say around this point, right, in some neighborhood of this point, in some neighborhood of this point, and in some neighborhood of this point. Can I approximate the systems around that neighborhood so that the behavior is preserved, right? So, around that equilibrium point, I know by these plots that that I can look at trajectories either coming back to the equilibrium or going away from the equilibrium point. Okay, so right. So, we find an approximation to this nonlinear system, and why linearization? Well, the differential equation for almost all processes are nonlinear, and as we will see, of course, we will restrict our discussions only to linear systems. The analysis and control methods, including stability analysis method, are much simpler for linear systems than for nonlinear systems. Okay, so local linearization, I now start with a system which of the form x dot equal to fx comma u. Okay, so I am also looking at a system with inputs, and suppose and also I do the approximation that at the equilibrium point f x star and u star it just goes to 0, at the right hand side just goes to 0 at the equilibrium point, so that x dot equal to 0 at x star and u star. These are the states at the equilibrium and the input at the equilibrium. Okay, so suppose now I start from u star, I start from x star, and if the initial condition is x star, I will always remain at the equilibrium point. That if I am at the equilibrium point, I will always remain at the equilibrium point. That is not interesting. Things get interesting when I do a slight perturbation, a downward perturbation at the downward position of a stable pendulum. It just comes back to the original position. Perturbation, if it is just here, it will always be here. Perturbation will change or make the story interesting. Okay, so with this I perturb the initial conditions, and I also perturb the input a little bit. Okay, and then therefore the corresponding output. So I look at the equations of the form x dot is f x comma u, y equal to h x comma u. Okay, so the corresponding output will be close to but not equal to h x star u star. Right? Everything is like around that little equilibrium point. How much now? What is the variation? How will x t and y t change when the equilibrium is perturbed by delta x and the input is perturbed by a delta u? Of course, we know now the approximations. I will just look at the Taylor series expansion about again I'll skip the steps here, but this is kind of good enough for us, right? So I look at delta x dot is a delta x plus bu, delta y is c delta x and du. This again just comes from a simple Taylor series approximation. Okay, the steps we will skip. Of course, we will use the properties that f x star u star is equal to 0. Okay, now for small variations around equilibrium point delta x, right, now I have a linear system A, B, C and D. These are familiar. Where do this A and B come from? These are just this is the Jacobian matrix of f with respect to x, this is the Jacobian matrix of f with respect to u, and similarly C comes as the Jacobian of h with respect to x, D comes as the Jacobian of h with respect to u. This is called the local linearization of 2 around the point x star u star. Okay. The details, the steps I am skipping, but we will just learn it by some examples. Okay, so I just look at the nonlinear equations of a simple pendulum. I also said b equal to 0 for simplicity. Okay, so what I now have is I can write this in the state space form like this. So this is x dot. So this is my f x u, there is a u here. So x dot, x1 dot is x2, x2 dot is minus omega square sine x1 plus u. Okay, so what does my local linearization say? I must just look at, so I just write down the f here. So f will be x1 dot is x2, x2 dot is minus omega square sine x1 plus u. Okay, so I do the Jacobian of this. So what will this be? I take so A is the Jacobian or the partial of f with respect to x. So I have x into f into variables x1 and x2. I will have df1 by dx1. So this is on the first term is f1, second term is f2, df1 by dx1 will be 0, df1 by dx2 will be 1. Again the partial of f2 with respect to x1, so there is a x1 here, so this will be minus omega naught square cos of x1, and then d of f2 by dx1, so this should be x2, right. This will be 0. Okay. Now I am looking at some arbitrary position theta naught, so this will be I just substitute. So all this I compute at x star and u star. Okay. Similarly, b will be the partial of f1 with u, there is no u term here, so this will become 0. Partial of f with u, there is this u term here, so this will become my. So all this now are constant matrices because I am evaluating this at x naught and u naught. Okay, so I look at what happens at the equilibrium point 0, 0. At 0, 0, I have a system which is like this. Okay, the eigenvalues are j omega and negative of j omega, which means that the system is marginally stable. Eigenvalues are also the poles of the system, as we saw in the previous lecture. For the equilibrium point pi 0, and also this will hold for minus pi 0, I will have my eigenvalues which are at omega and plus omega and minus omega. There is this eigenvalue in the right half plane or the pole in the right half plane. This means that the system is unstable. Okay. Now we can look at the phase plot, right, at around 0, 0, all the trajectories which were starting around 0, 0 were coming back to the point 0, 0. All the trajectories which were going away, which were around plus minus pi 0 were going away from the equilibrium, and this we called it therefore as unstable. Now this is the analysis of that. Locally I linearize and that behavior is preserved around that equilibrium point. Okay. So the behavior of the original nonlinear system around the equilibrium point is the same as the behavior as the linearized approximation via the Taylor series expansion. Okay. Now that is the magic here. That is the first method of Lyapunov, which says start with a nonlinear system, linearize it via its Taylor series expansion. If the linearized system is stable around that equilibrium point, the nonlinear system is also stable around that equilibrium point. And from now, when I say the system is stable, it is with respect to an equilibrium point, that the pendulum system is stable at the downward position. This is an equilibrium point. It is unstable at the upward position. So stability is also defined with respect to an equilibrium point now. Okay, so this is nice. So in general, how do I compute the Jacobian? So I will have x1 dot. A system of the form x dot equal to fx. So I am just assuming this input. So x1 dot will be a function f1 x1 till xn, all the way till xn dot will be a function x1 till xn. Okay, and this is how I compute the Jacobian. I can also now look at the simple example that we had, x dot equal to minus x. The Jacobian of this is minus 1. Okay. So this is my A matrix, eigenvalues are minus 1, so the system is stable. X dot equal to x, the Jacobian or A will become plus 1, eigenvalue is plus 1, so therefore unstable. Okay, so the linearization step, write down the nonlinear state space equations, compute the Jacobian matrix. So these are the 4 things that you need to compute: the A for the linearized version, the B for the linearized version, the C and the D for the linearized versions. Okay, compute the equilibrium point and then check for the eigenvalues of A at each of those equilibrium points. Okay, and then these are again local behavior, right? I am just looking at some small neighborhood around that equilibrium point. It is not a global thing that, oh, I did some linearization, the system is stable, therefore it is stable for the entire state space. It is not true, as we saw in the examples of the simple pendulum. Okay, in one of our earlier lectures, we looked at the predator-prey models, which were described by the Lotka-Volterra equations, where X was the prey population, Y is the predator population, and I have a growth rate. So if there is no predator, the prey will go unbounded. If there is no prey, the predator will just die down. But good things will happen if they are talking to each other, if they are in contact with each other, that the prey will die because the predator is feeding on it, and the predators will multiply because they have some food to eat. Okay, so for some values of alpha, gamma, delta and so on, this is how my behavior will look like, right. So I start from here and I am just kind of circling around this point, right. The populations will increase and decrease, there will be at some point of time more predators, more prey and so on. But there is a point here of interest, right, which is the equilibrium point, right. So the equilibrium point will be alpha over beta, gamma over delta, right. There is another trivial equilibrium point. It is a nonlinear system, it will have multiple equilibrium points. This is not interesting, right? There is no predator, there is no prey, okay, there is no dynamics, right. Interesting things will happen if there are non-zero predator and prey populations. So how do I look at it from a linearization point of view? So this is how my Jacobian will look like, this point, and the Jacobian now. So these are the equilibrium points. I just equate the right hand side of this expression to 0 to compute what my equilibrium points are. So this turn out to be something like this. Again, based on that this the eigenvalues will be on the imaginary axis, there will be some kind of a cyclic or a periodic behavior around this. Again, this is just a linear approximation. The nonlinear thing will not just go in circles, but some kind of a different kind of shapes, as you see here, right. The shape is mostly something like a triangular kind of shape. But the linear approximation will say some nice information that it will just be orbiting around that point. But if you start at this point, x equilibrium, y equilibrium, the population of the predator and prey will just be the same for all times t greater than 0. Okay. So the trajectories in the phase portraits around the coexisting point is similar both in linearized and the nonlinear system. It is not exactly the same, but it just has some kind of a periodic behavior. Coexistence is when I start with at the equilibrium position there are say some initial number of x and y, they will always remain at that x and y. And how do we do design in the state space methods? That is coming up. Thanks for listening.